Imagine you want to drive to the next town over. To get there, you need a 10-gallon tank of gas. But here's the catch. To carry that tank, the rules say you have to hitch a massive 1,000-gallon tanker to your car, filled to the brim with that same fuel. For 90% of the trip, you'll be burning fuel just to haul the weight of the tanker itself. It sounds like the fever dream of a mad engineer. Let's try another analogy. Imagine you need to get a tiny flash drive up to the 10th floor of a building. But instead of just putting it in your pocket and taking the stairs, you build a massive tower crane as tall as the building itself. A crane that spends almost all of its energy just lifting its own steel beams. And here's the catch. Your actual payload, that little flash drive, makes up a microscopic fraction of the entire structure. Now, this might sound like an absurd thought experiment, but it isn't. It is a perfect description of how every modern rocket actually works. The payload, whether it's a satellite or a capsule carrying astronauts, is just a tiny sliver at the top of a gargantuan machine. In fact, 90% of that machine's total mass is nothing but fuel. We watch these spectacular launches, the towering pillars of fire and smoke, and we see a triumph of engineering. And it is a triumph. But from the perspective of physics, it is a catastrophe. The figure sounds absurd, but it's the cold, hard truth. Over 90%. That is how much energy a rocket loses forever during every single launch. It isn't spent accelerating the payload, and it isn't used to overcome Earth's gravity. To be precise, all that energy goes toward one thing: blasting superheated gases out of the nozzle at terrifying speeds. Calculations show that reaching orbit should actually require 10 to 12 times less energy than the engines produce during the flight. The rest? It simply vanishes. In terms of efficiency, a modern rocket is comparable to a steam locomotive from the 19th century. We are sending humans to other planets using technology that is essentially stuck in the era of coal furnaces and smoke-belching chimneys. That realization led me to the question that sparked this entire investigation. How is it that we, a civilization capable of editing the genetic code and peering back to the very dawn of the universe, still rely on such a wasteful method to leave our planet? To find the answer, I decided to break it all down piece by piece. First, we're going to peel back the physics of this fundamental failure. There are two core reasons why rockets are so staggeringly inefficient. Then, we'll look at how engineers have tried, and are still trying, to fix the problem without changing the underlying concept. And finally, the best part, the alternatives. We're diving into the boldest, most ambitious ideas for reaching the stars, from massive space cannons and catapults to orbital elevators and rotating tethers. It seems simple enough. If rockets are this inefficient, we must have bad engines. We just need to invent something more powerful, something more fuel efficient. And after 70 years of the space age, you'd expect engineers to have solved that by now, right? Well, no. And that is perhaps the ultimate paradox. The problem isn't that our technology is lacking. In fact, modern rocket engines are nearly perfect machines. They squeeze every possible drop of energy out of a chemical reaction. The real reason for this staggering inefficiency lies much deeper. It isn't a failure of engineering, it's physics. The bottleneck isn't the hardware, it's the very physical principle of launching a rocket from the surface of the Earth. This isn't a bug we can patch or a mistake we can fix. It's a fundamental law of the universe we're forced to live with. It's like trying to lift yourself off the ground by pulling on your own hair. So if the problem isn't with the engines, but the fundamental principle itself, what exactly are these killer rules? Which laws of physics, specifically, force us to burn through tons of fuel for virtually no gain? As it turns out, there are only two, and they are both completely ruthless. The first of two ruthless laws is the very heart of rocket science, a curse known as the Tsiolkovsky equation. It sounds technical, but the underlying reality is simple and devastating. To get anywhere, a rocket has to burn fuel not just to lift its payload, but to lift every drop of fuel it hasn't used yet. Imagine having to haul an entire gas station on your back just to drive to the next town. The further you go, the lighter the load becomes. But at the starting line, almost all your energy is wasted just moving the fuel itself. It's a fuel-based Ponzi scheme. On paper, in a perfect world with zero air resistance and flawless engines, getting a spacecraft into orbit should only require burning 3.3 times its own mass in fuel. That doesn't sound too bad, right? But that's the theory. Here is the reality. Take the Soyuz spacecraft. It weighs just over 7 tons. To get those 7 tons off the ground, you need 282 tons of fuel and oxidizer. Hold on. 7 tons versus 282? That's 39 times the weight of the ship. Not 3, 39. Maybe that's just outdated technology? Fair enough. Let's look at Elon Musk's cutting-edge Crew Dragon. It weighs 12 tons, but requires about 480 tons of fuel to launch. The ratio remains exactly the same, roughly 1 to 40, or 1 to 39 if we're being pedantic. Decades of engineering breakthroughs, revolutionary materials, and advanced computer modeling, and yet we are still stuck in the exact same spot. We are still burning 40 barrels of fuel just to put a single barrel of payload into orbit. That was just the first problem. The second? It might be even worse. It's rooted in the very physics of jet propulsion. To push a rocket up, you have to hurl something down at incredible speeds, specifically searing hot gases. And that's the catch. Think of it like this. Imagine standing on a skateboard and throwing a heavy medicine ball as hard as you can. You'll roll backward. But most of the energy you just exerted didn't go into moving you, it went into accelerating the ball. Rockets face the exact same dilemma. Nearly all the massive energy generated by the chemical reaction is spent just blasting exhaust gases away at insane speeds. The rocket itself is left with the crumbs. Just how much are we talking? Brace yourself. Up to 80, sometimes even 90% of all the energy released by the fuel simply vanishes into the atmosphere along with the exhaust plume. Let's look at the big picture. 97.5% of a rocket's mass at liftoff is pure fuel. And of all that stored energy, 90% is spent doing nothing more than heating and accelerating the exhaust itself. It is catastrophically inefficient. We build these massive structures, packed with enough energy to power a small city, only to watch 99% of the entire effort burn up and vanish into nothingness. This specific double trap of physics makes space the most expensive real estate in the universe. Right now, launching a single kilogram into low Earth orbit costs anywhere from $3,000 to $30,000. 1 kilogram, about the weight of a small bag of sugar. And keep in mind, that's the budget option, the price for delivery just to the front door. From there, the costs only go up. This massive price tag explains why there is no room for dead weight in space. It is also why, in 1965, a simple sandwich triggered a full-scale federal investigation. Astronaut John Young famously smuggled a corned beef sandwich onto the Gemini 3 spacecraft. Once the crew hit zero-G, crumbs began drifting through the cabin, threatening to short-circuit the electronics or be inhaled by the crew. Today, the story is told as a classic anecdote, but the logic behind it was stone cold. Every gram on board costs a fortune, and every gram must be accounted for. An unauthorized sandwich that could cripple a multi-million-dollar spacecraft? That's no laughing matter. So, we're trapped, locked in by the fundamental laws of physics. You can't fix them, and you certainly can't improve them. They simply are. But in 70 years of the space age, haven't engineers found a way to at least cheat? Let's look at the most obvious path. Could we just build a better rocket? The answer seems obvious. To make a rocket more efficient, you simply build a more powerful engine. You refine it. You perfect it. And that would be a great plan if it weren't for one inconvenient truth. 95%. Not 5, not 50, 95. Modern liquid rocket engines are already operating at 95% of their theoretical maximum efficiency. This means we haven't just hit a ceiling in engineering, we've hit the hard limits of physics itself. There's almost nowhere left to go. It's like trying to make a glass even emptier when there's only a single drop left. But surely we're making progress. We hear about the triumphs of SpaceX and Blue Origin almost every day. Reusable rockets that touch down back on Earth. It feels like a revolution. Well, yes and no. Elon Musk's innovations are a brilliant solution to an engineering problem, but they don't change the underlying physics. They aren't making rockets more efficient, they're just making them cheaper. Instead of discarding a first stage worth tens of millions of dollars after every launch, they land it and fly it again and again. Imagine if airlines torched their planes after every single flight. That's exactly what we used to do. Reusability finally brings some much-needed common sense back to the industry, but it still can't break the tyranny of the Tsiolkovsky rocket equation. There is another path we could take, one that focuses not on being smarter, but on being bigger. We could simply build a massive rocket using the most inexpensive materials available. It's an engineering philosophy known as the big dumb rocket. The logic is simple. Use sheer scale to drive down the cost of every kilogram sent into orbit. You could even swap standard kerosene for high-energy liquid hydrogen to boost efficiency by another 50%. But when you stack all these improvements together, reusability, scale, and better fuel, the total cost only drops by a factor of 2 or 3. And honestly, that threefold reduction is the absolute best-case scenario under perfect conditions. For the industry, that's a giant leap, but for the future of space exploration, it's barely a drop in the bucket. We are still trapped. And this is where the ultimate trump card of 20th century science fiction enters the frame. The atom. Nuclear energy. If chemistry had hit a ceiling, maybe it was time to change the very foundation of how we move. The numbers look like magic. 1 kilogram of uranium, when fully split, releases roughly 1,000,000 times more energy than 1 kilogram of the most efficient hydrogen-oxygen fuel. 1,000,000 times. That isn't just an improvement, it's a leap into a whole different realm of physics. It's like comparing the strength of an ant to the power of a freight train. On paper, it seemed like the perfect solution. Just put a nuclear reactor on a rocket, and all your problems would simply vanish. But as always, the devil was in the details, specifically 2 of them, weight and radiation. The concept behind a solid-core nuclear engine is straightforward. You take a reactor, heat it until it's white hot, and pump hydrogen through it. The hydrogen hits temperatures of 3,000 degrees, roaring out of the nozzle to generate massive thrust. On paper, this design is 2 to 3 times more efficient than a traditional chemical rocket. But there's a catch. The reactor and its heavy radiation shielding weigh an enormous amount. Take the Phoebus 2A, the most powerful American prototype. While it produced 113 tons of thrust, the engine itself weighed nearly 20 tons. That immense mass effectively swallowed up any gains in efficiency. A rocket with a heart this heavy simply couldn't lift a meaningful payload off the ground. Then, there were the truly wild ideas. Take, for instance, the nuclear saltwater rocket. This concept used a solution of uranium salts dissolved in water, and on paper, it was a powerhouse, 20 times more efficient than a standard chemical engine, while requiring 90 times less fuel. It sounded like a dream. But there was a massive catch. This engine wouldn't just heat its propellant, it would literally spit radioactive decay products directly into the environment. We're talking about the deadliest exhaust in human history. Every single launch would have turned the pad, and the entire landscape around it, into a radioactive wasteland for thousands of years. So, is nuclear power in space a dead end? Far from it. We've simply found the right job for it. Nuclear reactors turned out to be nearly useless for lifting off from Earth, where you have to fight gravity's crushing weight with every ounce of power you have. But in deep space, they're perfect. Out there, they don't function as traditional engines. Instead, they act as onboard power plants, fueling electric thrusters on what we call space tugs. These engines produce a tiny amount of thrust, comparable to the force of a hairdryer. But there is a catch. They can run for months or even years. Bit by bit, they efficiently accelerate a spacecraft to staggering speeds. For a long-haul mission to Mars or Jupiter, it's the ideal solution. The atom found its place in the stars. It just wasn't the one we all expected.
So where does that leave us? Chemical rockets have been pushed to their absolute limit. Launching nuclear engines from the ground is either impractical or, frankly, lethal. The evolutionary path we've been following has hit a dead end. We are simply building more polished versions of a fundamentally inefficient tool over and over again. If we can't revolutionize the rocket itself, maybe we should rethink its hungriest, most wasteful component, the first stage. For decades, we've dreamed of literally firing cargo into space, as if from a massive cannon. But what if I told you this isn't just a dream? It's already been done, and the results were spectacular. Project HARP lived up to its name, the High Altitude Research Project. They launched scientific probes using a massive 36-meter gun barrel. A projectile weighing nearly 200 kilograms would scream out of the muzzle at over 2 kilometers per second, climbing to an altitude of 180 kilometers, soaring even higher than the International Space Station. It was simple, brutal, and highly effective technology. It seemed like the answer was right there, but the devil, as always, was in the details. Or, more accurately, in the G-forces. At the moment of firing, the projectile hit an acceleration of 15,000 Gs. 15,000. A single car crushing a human being is already fatal. But here, 15 tons of force pressed down on every single kilogram of cargo. Imagine a stack of 3,000 cars. A solid slab of steel might survive that kind of pressure. But a satellite? Every attempt to launch a 90-kilogram craft using the cannon ended in failure. The solid fuel inside simply buckled under the crushing acceleration, turning into a useless, mangled mass. This problem hasn't gone anywhere. Today, a company called Spin Launch is trying the same thing, only with a more elegant twist. They spin a rocket inside a massive vacuum centrifuge and hurl it into the sky at 2,100 meters per second. Once it reaches an altitude of 60 kilometers, the engines ignite to carry a payload of up to 200 kilograms into orbit. But the peak G-forces remain the same, climbing to nearly 10,000 Gs. That is fine for simple, rugged cargo, but sensitive electronics, solar panels, and human beings? They wouldn't stand a chance. It's a catch-22. To get rid of the rocket, we use a cannon, but the cargo still has to be built like a rocket just to survive the shot. Okay, if the problem is sudden, violent acceleration, could we just speed up more gradually? We can. To do it, we'd use an electromagnetic catapult, otherwise known as a mass driver. Imagine a long vacuum tube where magnetic fields propel an object forward, building its speed step by step. We could set the acceleration to whatever we want, even a human-friendly 3Gs. No crushing forces, no deadly pressure. Problem solved? Technically, yes. But as one problem vanishes, another, equally absurd, takes its place. The problem of scale. You can't cheat physics. To reach orbital velocity with low acceleration, you need a massive amount of runway. To get a payload up to speed at 30 Gs, which is already quite a ride, you'd need a track nearly 140 kilometers long. But for a passenger-friendly 3Gs, you'd need a track stretching 1,400 kilometers. To put that in perspective, it would be like building a perfectly straight, perfectly level vacuum tunnel from New York City all the way to Jacksonville, Florida. It's a brilliant solution, and on Earth, it's completely impossible. We've hit a wall. Again. We're left with a brutal trade-off. Either we crush our satellite into a pancake with extreme G-forces, Or we build a launch structure the size of a small country. Trying to punch through the atmosphere with brute force alone is a dead end. But what if we took a smarter approach? Instead of fighting the atmosphere, what if we cheated? We could use the air to our advantage, or at least get above the thickest part of it before we even begin. This concept is called an air launch. We take a carrier aircraft, strap a rocket to its belly, and climb to an altitude of 10 to 15 kilometers. We accelerate to nearly the speed of sound, and only then do we ignite the engines. Essentially, the airplane acts as a reusable first stage. And this isn't just a theory. Systems like Pegasus and Virgin Orbit are already proving it works. Decades ago, the Soviet Union even developed a project called MAX, a plan to launch a small space shuttle from the back of a literal giant, the Antonov 225 Mriya. On the surface, it seems like a massive advantage. You're starting where the air is already thin, and you're doing it with a significant head start in speed. But here's the strange part. The actual boost in altitude and velocity from an air launch accounts for only 4 to 5% of what you need to reach orbit. Wait, 4 to 5%? I double-checked the math. It's not a mistake. You save some fuel, sure, but it's hardly a revolution. So, what's the point? The goal isn't efficiency, it's flexibility. With a plane, you can launch a rocket from almost anywhere on the planet with a runway. You can target any orbital inclination you want. You don't have to wait weeks for the right launch window, and the weather on the ground? It barely matters. Air launch isn't a way to make space travel cheaper, it's a way to make it accessible and fast. It's a niche solution, but a vital one. Then, there's an even more exotic way to cheat gravity: beamed propulsion. Picture a spacecraft sitting on the launch pad with no engines and almost no fuel. Suddenly, a massive laser or microwave beam fires from the ground, striking the base of the craft. That beam flash heats the air underneath into a state of glowing plasma. The plasma expands in a violent explosion, kicking the craft upward. Now, imagine that happening thousands of times every single second. The ship essentially rides a pillar of fire, an engine fueled by energy beamed directly from the Earth. And it actually works. In laboratory settings, these models have already climbed dozens of meters into the air. But, just like the space catapult, we run into a massive problem with scale. A launch like this requires roughly 1 megawatt of power for every single kilogram of payload. To lift a tiny 10-kilogram satellite, you would need the energy output of an entire small city, all focused into one single point. Even then, you hit a ceiling. At an altitude of 15 or 20 kilometers, the atmosphere becomes so thin that the beam has nothing left to heat. The engine, quite literally, runs out of air. And here we are again, back at the same impasse. Cannons, catapults, air launches, lasers. Every one of these methods is an attempt to either punch through or bypass the thickest, most suffocating layers of our atmosphere. But there's a catch. Every solution births a new problem, each one just as daunting as the last. Essentially, all these ideas are attempts to smash through a wall, or maybe climb over it. But that wall, those first 100 kilometers of air, isn't going anywhere. So, what if we stopped trying to break it down? What if we built something so immense that it begins here on Earth and ends in the reach of space? So, what if, instead of trying to punch through the wall of the atmosphere, we built a ladder that simply steps over it? Oddly enough, the first answer to this question isn't vertical, it's horizontal. Imagine a bridge 2,000 kilometers long, roughly the distance from New York City to Denver. One end is anchored in the Pacific, the other is too. But in the middle, the bridge arches upward, reaching 80 kilometers into the sky. Up where the sky turns ink black and the stars stop twinkling. How does a structure like that even stay up? The truth is, it doesn't. It is held aloft by nothing but pure motion. This is the launch loop, a 2,000-kilometer vacuum tube suspended 80 kilometers above the Earth. Inside that tube, through a total vacuum, a closed-loop ferromagnetic cable hurtles at 12 kilometers per second. It acts like a river of metal, using its intense momentum to push the tube upward, refusing to let it fall.
This isn't just a building. It's kinetic energy, tamed and harnessed.
This soaring track uses an electromagnetic catapult to sling the ship forward. The G-forces top out at only 3 Gs, perfectly tolerable, even for an average person. The ship simply glides along rails that stretch all the way to the edge of space. The price tag? Tens of billions of dollars. That sounds massive, but it means the cost of putting a single kilogram into orbit plummets to $300. And if you keep the cargo moving in a constant, steady stream, $3. Not 30, not 300, just 3 per kilogram. That's the price of a bag of apples at your local supermarket. Suddenly, space isn't just accessible, it's cheap, it's routine. But even an idea this ambitious is just a warm-up, a prelude to a project on a truly massive scale. What if we didn't just build a bridge? What if we built a ring, one that circles the entire planet? Sitting 500 kilometers above the surface, this is the orbital ring. Like a satellite, it rotates, but at a blistering pace. It moves much faster than a standard orbit requires, roughly 10 kilometers per second. At these speeds, centrifugal force doesn't just counter gravity, it pulls the ring outward with such intensity that it strains toward deep space. It's that very tension, that massive outward pressure, that holds the entire structure in place. From this rotating ring, we can lower platforms that hang perfectly still relative to the Earth. And from these platforms, a cable descends, stretching 500 kilometers all the way down to the planet's surface. Suddenly, you have a functional elevator. But it isn't just a trip into space, it's a gateway to an orbital superhighway encircling the entire globe. The cost to build it? Estimates vary wildly, anywhere from $250 billion to $3 trillion. We are talking about the entire budgets of sovereign nations, projected decades into the future. But if we actually build it, the price of delivering a single kilogram into orbit drops to just 30 cents. 30 cents. That isn't the price of a bushel of apples. That is the price of a single apple. It feels like the ultimate solution. And yet, there is something haunting about these gargantuan, rotating structures. They feel too complex, too brutal. Surely, there must be a simpler path. A more elegant one? There it is. The most famous, most beautiful idea of them all. The space elevator. No spinning rings, no supersonic tethers, just a single cable stretching from Earth's surface to geostationary orbit, nearly 36,000 kilometers up. And it goes even further, reaching out 100,000 kilometers to a counterweight, perhaps a captured asteroid. As this weight rotates with the planet, centrifugal force pulls the cable taut like a string. It just hangs there, vanishing into the blackness of the sky. You step into the cabin at sea level. There's no roaring engine, no crushing G-forces. The doors glide shut, and you simply begin to rise. It's smooth, just like a regular elevator. At first, clouds drift past the window. Then the blue sky slowly deepens, fading to purple, and finally into a charcoal black velvet. Against that darkness, the stars ignite, steady and still, without a hint of flickering. Below you, the massive blue world slowly turns. The journey takes a week, but it changes everything. There is, of course, a major problem: the material. A steel cable would simply snap under its own weight. To keep it from breaking, you would have to taper the design, making it incredibly thick at geostationary orbit and narrow at the Earth's surface. But the math reveals a catch. The cable's widest point would end up larger than the observable universe. It sounds like a joke, but it's pure physics. We need a material roughly 20 times stronger than anything currently in existence, something like carbon nanotubes. If we could ever mass produce them, the entire cable would weigh about 1,000 tons. To be clear, that is just the mass of the cable itself, not counting the climbers or the counterweight. But at that point, we are looking at a solvable engineering challenge. It is expensive and immensely difficult, but it is possible. So, it seems simple. We just wait for a breakthrough in material science and the dream becomes reality. Right? Wrong. The biggest hurdle for a space elevator isn't the strength of the cable, or even the price tag. It's the fact that we aren't alone up there. Think of the elevator cable as a single, stationary thread stretched across the busiest traffic lanes in orbit, low and medium Earth orbit. These regions are already crowded with thousands of active satellites and millions of pieces of space junk. Every single fragment is essentially a bullet, screaming through the void at several kilometers per second. Their paths will constantly intersect with this immovable line. It isn't a question of if, it's a question of when. Building an avoidance system for a cable thousands of kilometers long is, quite frankly, impossible. Sooner or later, a collision is inevitable. The impact snaps the cable. The lower section, 36,000 kilometers long, begins to fall. It lashes around the equator like a colossal, fiery whip, obliterating everything in its path. Meanwhile, the upper half and its counterweight drift into a higher orbit, turning into yet another massive piece of uncontrollable space junk. It is a catastrophe on a planetary scale. The space elevator is the most elegant and most deadly trap imaginable. It would be perfect for a barren world, but for ours, already swarming with a cloud of satellites, the project is a suicide mission. Once again, we've hit a dead end. Even the most ambitious and beautiful ideas eventually shatter against the wall of reality. It seems every stairway to heaven is either far too expensive or far too dangerous. But what if we kept the cable, but didn't drop it all the way to the surface? What if, instead of an elevator, we built a rotating skyhook? The dream of a space elevator has always hit a wall because of one specific flaw: that massive cable reaching all the way to the surface. It's simply too long and far too vulnerable. But what if we ditched that part of the design? Instead of trying to build a bridge from the ground to the stars, what if we just lowered a rope ladder from orbit? This is the concept of the Skyhook. Imagine a satellite orbiting 600 kilometers above the Earth, unspooling an ultra-strong cable 500 kilometers long. The tip doesn't actually touch the ground. Instead, it dangles at an altitude of 100 kilometers, right at the edge of space, where the atmosphere finally begins to thin into nothing. The secret lies in the rotation. The entire system, the satellite and its long tether, spins around its center of mass like a colossal sling. It rotates with such intensity that the very tip of the cable, a hook positioned 100 kilometers above the Earth, whips through the sky at 3.5 kilometers per second. That isn't quite orbital velocity yet, but it's nearly halfway there. This is where things get elegant. Instead of a massive rocket, a hypersonic aircraft takes off from the ground. It arcs upward on a ballistic trajectory, like a stone tossed into the air, climbing toward that 100-kilometer mark. At the peak of its arc, for one brief moment, its speed perfectly matches the end of the tether. They dock. The aircraft hands off its cargo, and the rotating hook, acting like the arm of a hammer thrower, simply whips the payload away, vaulting it into a stable orbit. For the passengers or cargo on board, the experience feels remarkably smooth. There are no punishing G-forces here, nothing like being shot out of a cannon. The entire process of the ascent and the handoff generates no more than 3 Gs. That's roughly what you'd feel on a standard roller coaster, well within the limits of human endurance. Imagine boarding a hypersonic aircraft, soaring into the stratosphere, and gently docking with the end of a cable. Then, almost effortlessly, you're swept upward. No deafening roar, no pillars of fire. Then there's the economics. The estimated price tag for the entire project? $50 billion. Now, that's an optimistic figure to be sure. It doesn't account for the inevitable R&D risks. But even if that cost doubles, it's still orders of magnitude cheaper than a traditional space elevator. The real breakthrough, however, is the launch cost. Once operational, the price of sending a single kilogram into orbit could drop to just $10. Think about that for a second. Not $1,000, not even $100. 10.
That doesn't just make space accessible, it makes it affordable.
But the true potential of this technology lies far beyond Earth. On the Moon or Mars, worlds with little to no atmosphere, the Skyhook evolves into something entirely different. We can spin it with such precision that the tip of the tether reaches a dead stop relative to the ground the moment it touches the surface. It could literally crouch to snatch cargo directly from a launch pad. Then, with one sweeping rotation, it could hurl that payload into orbit, or even slingshot it toward another planet. At this point, it's no longer just a hook, it's a cosmic crane. It wouldn't just launch missions, it could catch incoming spacecraft too, gently lowering them all the way down to the surface. And that brings us to the ultimate question. The Skyhook seems like an elegant, cost-effective, and remarkably safe solution. It sidesteps the massive engineering hurdles of both space elevators and orbital catapults. On the surface, it feels almost perfect. So, why are we still burning hundreds of tons of kerosene every time we want to leave the planet? If such brilliant engineering concepts are within our reach, why are we still clinging to technology that is essentially a century old? It's time to look at the big picture. So, here we are. After the cannons, the catapults, and the elevators stretching into the stars, the answer to our ultimate question turns out to be frustratingly simple. It can be summed up in a single sentence. There is no such thing as a free ticket to space. Reaching orbit is such a massive undertaking that every solution demands staggering, almost unthinkable compromises. This isn't a choice between a good option and a bad one. It's a choice between different flavors of disaster. Let's look at them exactly as they are. No sugarcoating. The space gun? The crushing G-forces would pulverize any crew and delicate electronics, turning them into little more than high-tech dust. An electromagnetic catapult? That requires a megastructure stretching for hundreds of kilometers, a project that would be incredibly vulnerable and insanely expensive. A space elevator or a Skyhook? They're brilliant concepts, but we simply don't have the materials to build them yet. The tether would need to be stronger than anything we've ever manufactured. In fact, it would have to be stronger than anything the laws of chemistry even allow to exist in our macroscopic world. And the nuclear engine? It works, but the trade-off is radioactive fallout and the violation of every international treaty on the books. Every beautiful idea carries its own ugly price. Against that backdrop, the rocket suddenly doesn't seem so stupid anymore. Sure, it's inefficient. Yes, it hauls fuel just to haul more fuel. It's like trying to scale a mountain while lugging a heavy ladder on your back. But it has one massive advantage. It works. Right now. It doesn't require miracle materials from the future. It doesn't crush its pilots into pancakes. It's versatile, capable of hoisting anything from a tiny satellite to a massive space station into orbit. You can launch it from almost anywhere on the planet. It isn't an elegant solution. It's the ultimate compromise. Given our current technology, our materials, and our limitations, the chemical rocket is the most balanced, most practical way to reach space that we have. But this isn't the end of the story. It's only the end of the first chapter. Rockets are going to be with us for a long time. They're perfect for scouting, for taking those very first steps. But for true space colonization? For lunar cities, terraforming Mars, or moving heavy industry beyond our biosphere? Rockets just won't cut it. The economics don't work. The cost of hauling every single kilogram into orbit will always be too steep. And when the stakes finally get high enough, we'll have to revisit those crazy ideas. We're going to need elevators, catapults, and skyhooks. Rockets helped us climb out of our cradle, but to learn how to walk, we'll have to build something entirely different.